primary purpose of the talk is to talk about the ASA Statement on p-values, which came out last year. And we're going to talk about it in the context of impact evaluations. The statement applies to all uses of p-values, but that's a little abstract, and I think that makes it a little bit hard to understand how it applies to any particular type of work, and so we're going to focus on impact evaluations in this talk. Overview of the talk here. I'm going to start off just defining what a p-value is and what the related concept of a confidence interval is. These will be familiar definitions, I think, to a lot of folks, but I think it's good to start with something familiar. I'm going to give you sort of the, I guess you might say the tweet storm version of the ASA statement, some of the problems with p-values. So I won't go into a lot of detail. It's a lot of stuff in their statement. But then I'll go into two specific issues related to p-values that I think are particularly relevant to impact studies. The first issue is that when we conduct hypothesis tests with p less than 0.05, declaring that a significant effect, if we misinterpret that as being the probability that an impact is due to randomness alone, if we misinterpret it, then we will, in many cases, severely understate the probability that impact is due to randomness alone. So we will essentially have many more false positives, many more false discoveries than what we realize. On the flip side, there are contexts in which testing with p less than 0.05 can lead us to missing the detection of important effects. And depending on the context, we might want to strike different balances between those two types of mistakes. So that will be really the meat of the talk. After I go through those issues, I'm going to provide a lot of suggestions for what we might be able to do in our own work. And I think part of the good news that I will preview now is that I think we already do a lot of very good things in our studies, both in terms of design and analysis. And that part of what we need to do in response to this ASA statement on p-values, I think, is to just be a little bit more mindful in packaging and presenting what we already do. But then there are some other things we need to do that we maybe don't do now. So I'm going to start off here with a definition of a p-value. And this definition is probably familiar to a lot of folks who have taken a intro stats class. And I'll just give a little warning to anyone who might want to present a definition of a p-value, and we'll see if I can avoid the pitfall that I'm going to describe. If you stick to what's on this slide, you'll be fine. The problem is, as soon as you start to say too much, you need to know when to stop talking when you define a p-value. Because if you start to try to convert it into normal talk, that's where you can go wrong. So let's see if I can avoid that pitfall. We calculate an impact for our study, and we'll call that my estimate. The p-value is the probability that an impact greater than my estimate would occur by chance when the true impact is 0. So I'm going to describe this histogram that I made. On my computer, I summoned out of the ether a bunch of individuals who I then randomly assigned over and over again to a treatment and control group. And there was no intervention, so there was truly no effect. Every time I randomly assigned them, I calculated an impact on some made-up outcome, and I recorded that impact. So all of those impacts are due to randomness alone. That's the only thing that is resulting in an impact. And the histogram shows you the distribution of those impacts that are due only to randomness. The p-value is the proportion of those randomly generated impacts that are larger than my estimate, the estimate for my original first attempt to do this. So that's a p-value, and I just have to stop talking, because if I say anything else, I'll get it wrong. There's a related concept known as a confidence interval. This is also something that I think folks are pretty familiar with. I just want to point out some things about a confidence interval that I'm going to show a picture of confidence intervals. A confidence interval is the result of a process. We really want to focus on the process when we think about a confidence interval. The same is true of p-values and hypothesis testing, but it's the result of a process. The confidence level, which is the number that you usually hear attached to a confidence interval, numbers like 95%, 99%, 80%, that is a characteristic of that process. And so something that is correct to say about a confidence interval, you can say that a 95% confidence interval is an interval that is constructed in such a way that it contains the true value of the population parameter, which might be average height, it might be impact of a program, 95% of the time if the experiment or the study were repeated many times. So what does that mean? Well, still operating in omniscient mode on my computer, I replicated a study several times, in this case just 10 times, and in each case I randomly sampled from a larger population a group of people, and I calculated some mean of their outcome. Because I'm generating the data in this exercise, I know what the truth is, and the truth is 0, and the truth is indicated by that bright red horizontal bar on the figure. Then for each replication of this mythical study that I was conducting, I calculated both an 80% confidence interval, which is displayed in orange, and a 99% confidence interval, which is displayed as orange plus the extra blue. And what you can see from these replications is an illustration of that process that I was talking about. And you can see the characteristics of the process play out in the figure. So for the 80% confidence interval, the orange intervals, you can see that there are 2 cases, 2 out of the 10, where they do not include the true value of the population parameter. So the orange intervals for case number 9 and 6, the orange does not include that red line. So that's an example of how an 80% confidence interval is going to miss including the true thing 20% of the time. The 99% confidence interval includes it every single time, and I just got kind of lucky there, but this was only 10 replications. And you can see on replication number 9, it gets close to missing it. And so what you have to keep in mind when you're constructing a confidence interval is that although you only see the individual confidence interval you construct, so maybe you're study number 9, keep in mind that there's a process, and if you had different data, the ends of that confidence interval will move around. So that is a confidence interval, and that was a p-value. Those were the things that they are. Now I'm going to point out what they are not. So the p-value is not the probability that the impact is 0. Remember that we assume that the impact is 0 when we calculate the p-value. The p-value is also not the probability that the estimated impact is due to randomness alone. Again, we're assuming that the estimated impact is due to randomness alone when we calculate a p-value. There are a lot of variations on this, and the ASA statement lists like 25 different variations on wrong ways to say a p-value, so you can go look at them all. And it's, I don't know, it's a little not fun to read, because every one of them, they like say it and then they like, no, with an exclamation point. So it seems a little pedantic in some ways. But so I didn't want to go through all 25. Regarding a confidence interval, we cannot say that the true impact lies within our specific confidence interval 95% of the time. The point here is to remember that it's the confidence interval that is random, not the true impact. The true impact is fixed and sadly unknown, unless you use my computer. I just want to point out at this point that this might seem like a bunch of persnickety, pedantic wordsmithing. It might seem that I'm making a big deal out of very subtle differences in wording and where you stick a comma. And generally, I would not want to do that, but it turns out in this case that it actually does matter. Like the wording and where you stick commas changes things from conditional probabilities to unconditional probabilities, And there are subtle differences in the meaning, or seemingly subtle, that are actually really big differences. And I'm going to be showing you how big these differences are in the talk. But I just want to let you know right now, I'm not just being a persnickety wordsmith. These differences actually do matter. So the TweetStorm version of the ASA statement on p-values goes like this. The research community has sometimes relied too heavily on p being less than 0.05 as the way to determine which impacts reflect true impacts, which impact estimates reflect true impacts. Determining the believability, so do we believe this impact is real, and the substantive importance, so maybe it's real, but does it matter, of an impact estimate depends on a lot of things, and the p-value is probably not at the top of the list of the things that it depends on. The ASA statement makes the point that p-values are easily misinterpreted, and this gets back to the thing I was saying about the persnickety wordsmithing. It's easy to confuse what a p-value is with some things that sound very similar but are actually very different, and so that makes it easy to misinterpret what a p-value is. P less than 0.05, using that as a bright line demarcation between true effects and non-true effects can lead to what has been called a replication crisis in many fields. This came up in psychology, for example, where a lot of things that people really believed were established in research, a lot of findings they really believed were established in research, could not be replicated. And so there's a belief that the use of p less than 0.05 as a sort of bright line indicator of statistical significance has contributed to that. Why? Well, publication bias is one reason. So there have been in the past and perhaps in the present journals that if you submit a finding that is not statistically significant, they won't publish it. And so then nobody realizes that this thing wasn't effective. So if you do 100 studies of it and the only ones that get published are the ones that show statistically significant effects, then you're going to have a very skewed view of the effectiveness of a given intervention. There's also something called p-hacking, or in some fields it's known as data mining, but data mining in a bad way as opposed to a good way. And what happens here is that either consciously or unconsciously, researchers will start to make a whole bunch of different analytic decisions in order to get a p-value move from 0.051 down to 0.049. We don't do that because we're good, but there are people who do that, and that is bad. Some other specific issues. So using p less than 0.05 can lead people to misinterpret and overestimate the probability that a statistically significant impact is real. So in other words, p less than 0.05 isn't necessarily as conservative as people might think. On the flip side, sometimes p less than 0.05, using that as that bright line indicator, can lead us to miss some important impacts. So we can make the opposite mistake. We can have false discoveries. We can also have false non-discoveries or missed discoveries. Statistical significance does not necessarily equal substantive significance. The size of an impact estimate matters. To me, this seems like kind of an obvious point, and it's not a scenario I've ever encountered. I think this is basically an overpowered study, and my career has been spent listening to people smack me around and tell me that my study is underpowered, so I don't have a lot of experience with this. But if you analyze really big data sets, then you could end up seeing relationships in the data where you have statistical significance, but the substantive significance really isn't there, and so you wouldn't want to make a big deal out of it. P-value does not reflect errors from non-random sources, and I think we all know this, but I think it's worth just reminding us of this. So you could have a p-value that's less than 0.05, but that doesn't mean your impact estimate is unbiased. It doesn't mean that you didn't have non-response bias, selection bias, researcher bias. There are a lot of ways that a finding can be wrong or not very credible even if the p-value is low, and that's because the p-value is only focused on errors, controlling errors due to randomness. All right, so that was the tweet storm. Now I'm going to get into more detail on what I think is probably, if there was one biggest issue, I think this is probably the biggest issue. This is the thing associated with the replication crisis. Very often, we take a p-value and we want to say that it is the probability that an impact is due to randomness alone. We want to write in our report, well, we've got a p of 0.04, and what that means is that there's a very low chance that this impact could be due to randomness alone. A lot of times we want to say that. I did not go back and look at my past reports to see if I've said it. I might have, because I have not been particularly conscientious about this issue until this statement came out. So it's entirely possible that I've made such statements, and it's kind of something you'd like to be able to say. And it just turns out that's really not true. And so I'm going to walk through an example here to illustrate what this probability actually is. So it's not a p-value. I'm going to show you what it actually is and how you might calculate it, and I'm going to contrast it with what the p-value is. Okay? So I think this is really easiest to do with an example. I tried to make the example specific enough that it would make sense to people. I didn't want to make it so specific that people would start arguing with like practical details. So I'm not mentioning a field or anything like that. You know, I don't want anyone saying, well, in labor, we would never do that. So it's vague, but hopefully just specific enough. So imagine that there's a federal grant program funding 100 locally developed programs. And the truth, which is unknown to us mere mortals, is that 10 of those 100 programs have meaningful effects and 90 of them have no effect. So let's say that's truth. Ideally, we would study all of these. That would be what's in the best interest of our stock price and science. But we only have enough money to fund one RCT. And so we're going to have one randomly selected RCT or one randomly selected program where we're going to conduct an RCT. And we're going to conduct this study as we always do. We're going to test with significance at 0.05. And it's going to be a well-powered study. We're going to have an 80% chance of detecting the smallest meaningful effect. Okay, so this is going to be a good study. So key numbers, 100 programs, 10 have meaningful effects, 90 don't, 5% significance, 80% power. We're going to reach our hand into a giant barrel of studies and pull out a study. So here is my representation of the barrel of study apples. There are 100 dots here in the barrel, each corresponding to a study that we might pull out. And they're color-coded, and so I'm going to walk you through this. We know that 10 of these would-be studies are of interventions that have significant impacts, or real impacts, sorry, real meaningful impacts. And because we have 80% power, we know that we, in expectation, would detect 8 out of those 10 impacts. So the green dots correspond to the studies of interventions where the intervention both had a meaningful effect and we were able to detect it. Those are the green dots. The black dots are studies of interventions that had a meaningful effect, but we were not able to detect it. So that's our type 2 error rate, which is 20%. The gray dots correspond to the large number of studies that would be conducted in which the intervention had no effect and we had a statistically significant impact. So those are situations where we're not making a mistake on the rejection of the null side. Then the red dots are studies where there really isn't an effect, but we have a statistically significant effect. So truly there's not, but we have a statistically significant effect. And that is driven by our 5% alpha. So out of those 90 studies where it's not effective, 5 of them, actually 4.5 if you take 5% of 90, but I rounded up. So 5 of them, statistically insignificant effect. So now let's do a little calculation. What's the probability, if you have a statistically significant impact, what's the probability that it is due to randomness alone? What's the probability of that? It's not 5%. What it is you need to calculate a ratio. You need to, in your denominator, calculate what's the total number of studies in which we would have a statistically significant impact? So we're going to add up the reds and the greens. And so that is 5 plus 8, which is 13. Then in the numerator, we need the number of studies in which we have a significant impact that's not real. That's the reds. All right? So we take 5 divided by 13, and that is 38%. So when we have a statistically significant impact in this scenario, it does not mean that there's a 5% chance that the impact is due to randomness. There's a 38% chance that the impact is due to randomness. So that's an example of how very different the probability that an impact is due to randomness is from a p-value, which is really kind of sad. So if p is less than 0.05, that does not mean that there's a 5% chance that the estimated impact is due to chance. Calculating the probability that a significant impact is due only to randomness requires more information. We need to know what proportion of programs in some relevant population of programs have meaningful effects. So what we really want to know is not the p-value. What we want to know is something that some people call the false discovery rate. It could also be called the false positive rate. And this calculation draws on, well, there are multiple factors that affect this. And I've got it written out here. So a discovery, so-called discovery, occurs when p is less than 0.05 or whatever alpha value we choose. Some of these discoveries will be false. The false discovery rate is the number of false discoveries divided by the total number of discoveries. And so that's what I did on the previous slide. It was red in the numerator and red plus green in the denominator. That's the false discovery rate. It turns out that we can write this in terms of alpha, which is our significance level, and power, which was 80% in the example, and then this thing I'm calling Peffective, which is the proportion of interventions from some population that are truly effective, which in my example was 10%. So if you plug in the 0.05 and the 0.10 and the 0.8 into this formula, you end up with the false discovery rate, and that's the exercise we went through in the graphical example. Now, alpha and power are design parameters that we control, and so that's easy to come up with. But this Peffective thing, that is not as easy to come up with. We don't know that from our own study using our own data. We have to essentially take a guess or a guesstimate of that, and that's what's hard. So Peffective depends on a variety of things. There's going to be, or it could be informed by a variety of things. There's going to be a literature on the effectiveness of similar interventions, potentially, and that could provide you with some guide as to what Peffective might be. The strength of your intervention logic model, a more compelling logic model might push you in the direction of thinking that Peffective is higher. The quality of the intervention implementation, higher quality means Peffective is higher. Nature of the contrast with the counterfactual. If it's, for example, math curricula A versus math curricula B, that's a smaller contrast than math curricula A versus Scooby-Doo. So focusing on the magnitude of the contrast also affects Peffective. Now, estimating this Peffective thing, which is analogous to what a Bayesian would call a prior, this can be imprecise, to say the least. There are a lot of mistakes that a person could make in estimating this Peffective thing. But if you really want to know the probability that your impact is due to randomness alone, then it's actually much better to take a stab at estimating Peffective than it is to just misinterpret the p-value as being the false discovery rate. Because misinterpreting the p-value as the false discovery rate is way worse than picking a bad value of Peffective. So let me give you an example of how you might try to go about estimating Peffective. And I say it in the slide, and I'll emphasize it. This is a quick and dirty analysis that we did here to just show how you might estimate Peffective. So we looked at a whole bunch of impacts from the What Works Clearinghouse database of impacts. And we did this very thoughtlessly. I mean, if you were to do this in real life, you'd want to be more careful. But we just focused on all the impacts that meet standards with or without reservations in the clearinghouse, and we looked at distributional properties of those impacts. And we found that half of the impacts were greater than 0.13 standard deviations, and 25% of impacts were greater than 0.35 standard deviations. So what that means is if you think that 0.13 standard deviations is a meaningful effect, then the probability, Peffective, of detecting a meaningful effect, your estimate would be 50%. If you would say that 0.35 standard deviations is a meaningful effect and you want to power your study to detect that, then Peffective would be 25%. If you're going to do this in real life, you'd want to be more careful than what we did here and more thoughtful. But this is an example of something you could potentially do. A related concept is the false non-discovery rate, and this is just the analog to the false discovery rate. It's the probability of missing a real effect. I just want to throw that out there because I'm going to include it in a table, so it's got to be defined. So here I've just got a small little table showing trade-offs. I'm showing how Peffective relates to the false discovery rate and the false non-discovery rate, holding alpha constant, a sample size constant, power constant. So as you can see, if Peffective is low, 10%, which is what I assumed in my example where I said that 10 of the 100 programs actually had an effect. So if Peffective is 0.1 and you test with alpha equal 0.05, your false discovery rate is going to be 36%. That's a little different than my earlier slide, but that's because the earlier slide I was like rounding decimals, so don't worry about it. So your false discovery rate will be really high. Now, if you could convince yourself somehow that Peffective is 0.5, then testing with alpha equal to 0.05 will lead you to a false discovery rate of 0.06 in my little calculation, which is pretty much the same thing. So if half the things that you evaluate are truly effective, then it works out that misinterpreting the p-value isn't going to hurt you so much. I don't feel that optimistic, actually, about the things that I've evaluated over the course of my career. I really just don't think that half of them were effective, but, you know, different people work in different fields, different contexts. Maybe there are situations where that's a reasonable assumption, something you have to figure out. But you can see that number really drives the false discovery rate and the false non-discovery rate, basically flipping them around. Okay, so that was the issue of the false discovery rate and how misinterpreting the p-value to be the false discovery rate could really lead you down a bad path. Now I'm going to just completely turn everything on its head, and I'm going to worry about something else entirely, which is missing important effects, which is almost the opposite problem. So now I'm going to worry more about the false non-discovery rate than the false discovery rate. We need to think about how do we want to balance different error types. The hypothesis testing framework in which we declare an impact to be significant with p less than 0.05 is focused on minimizing basically false discoveries or type 1 errors. The idea here is maybe that the status quo seems to work and the cost of change is high, or these findings will have widespread disruptive consequences. So we really want to minimize the probability of a false discovery. And actually there are folks out there who argue that instead of p being less than 0.05 as the cutoff, it should be p less than 0.005 or 001. That should be the definition of statistically significant. And that recommendation arises from a focus on really controlling the false discovery rate at a level of 0.05. And there are contexts where that is probably appropriate. But there are also other contexts. So suppose we're in a situation where maybe there's some dissatisfaction with the status quo. Maybe the status quo isn't something we're so eager to defend. But there are also non-ignorable transition costs. So we're not in love with the status quo, but we don't want to completely capriciously throw it overboard. And we are concerned about the cost of missing effective alternatives. So this is more like a balanced scenario. In the first scenario, we're really focused on defending the status quo. Here, we're kind of like, it could go either way. And then a third scenario, suppose that there's really no strong reason to stick with the status quo. Maybe there isn't even a status quo. We have to make a choice between two alternatives. A choice is going to be made regardless of whether there's research or not. And so that's almost the exact opposite of the first scenario, where we really don't care about type 1 errors at all. So I'm going to give 2 examples corresponding to those second 2 bullets, because I've already covered the first one in the first part of the talk. And so this first example, this is a Medicare example. I mostly got this example from Randy. I don't know anything about healthcare. Turns out healthcare is really complicated. Who knew? And so I'm going to walk through this, but I can't answer any questions about it. According to Randy, we need to reduce Medicare costs, I guess. And past research has found that 60%, let's say, I think that's a made-up number, of interventions involving significant changes in care delivery, example ACOs, I don't know what that stands for, have reduced Medicare costs by at least 4%. A new study is being designed to test whether an intervention involving stronger financial incentives for changing care can achieve similar effects. So in this case, this is a scenario where we think that assuming a pretty high level of P effective makes sense. So we're assuming 0.6. So we're looking at an intervention that is pretty similar to a lot of other interventions that have been found to be effective. And so we think that the proportion of like interventions that's effective is pretty high. And we're not thrilled with the status quo, although we don't want to be capricious in overturning it. So if we test with alpha of 0.05, our false discovery rate is actually going to be a little less. It's going to be 0.04, but our false non-discovery rate is going to be 0.23, and that seems too high. So this is a scenario where we don't want to use the typical design parameters. Instead, we want to change the design parameters, and I had to end up tweaking the sample size a bit. So instead of testing with alpha of 0.05, we'll test with alpha of 0.15, nudge the sample up a bit, and now we're in a situation where the false discovery rate and the false non-discovery rate are more or less equal, which in this context seems like a more reasonable balance between those two types of mistakes. And now here's an example of the last bullet, where we're going to make a decision no matter what, regardless of whether there's research. This is an example that probably is more applicable to research that's informing internal processes. So maybe you have, for example, a school district that is trying to figure out what they want their new math curriculum to be, and they've whittled it down to 2 alternatives. They're pretty much indifferent between these 2 alternatives. In the absence of research, they will effectively, though not literally, flip a coin. And we want to see, well, can research improve this process? So in this example, we're going to ignore statistical significance. We're not even going to look at the standard error. It's going to be driven entirely by the point estimate. So this is polar opposite of the usual worries. And I'm going to compare 2 processes for making decisions, a coin toss to research. And we're going to see how much research can beat a coin toss over the long run. So again, this is focused on improving internal processes. We're not going to go out to the world and tell everybody that they should do whatever it is our study says. This is going to be a process that you repeat over and over again inside an organization to hopefully move them over time in a better direction. So the probability of picking the winner between 2 options with the coin toss is 0.5. I didn't have to simulate that. I figured it out myself. I used a simulation then to figure out the probabilities of research picking the winner, and the expected outcome benefit from beating the coin. And I had to make some assumptions for the simulation. So I assumed in 20% of all cases, so all the decisions that are going to be made, the difference between the alternatives is greater than or equal to 0.2 standard deviations, and that this true impact across the studies that we'd be doing is normally distributed. And what I find is that even with just 20 units randomized, so like 20 students randomized, we can beat the coin a little bit. We'll pick the winner 60% of the time as opposed to the coin that'll only get 50% of the time. And we would expect that to improve outcomes by 0.02 standard deviations relative to the coin. And as we start increasing our sample size, we can see our chances of picking the winner start going up, and our expected benefit relative to the coin starts going up. And at least to my eye, the n equals 100 in this scenario seems like a pretty good landing place. We beat the coin by a fair margin, and we improve outcomes by 0.04 standard deviations. And we'd have to really crank up the sample size to start moving it beyond that. So that kind of seems like the sweet spot to me in this case. But in any event, this illustrates that there are contexts where you just don't care about statistical significance, and that's going to lead you to a very different design and sort of way to interpret findings. And so p less than 0.05 can be just wrong in all sorts of different ways depending on your context. In some cases, p less than 0.05 isn't conservative enough. In some cases, it's too conservative. The message really is you just need to think. You need to think about what's the right balance of trade-offs in your situation, and then calculate the error rates that are appropriate. So conclusions. Statistical inference is hard. Answering questions like, what did we find? Do we believe it? What should we do? This is very difficult. It's difficult for a couple of reasons. One, we never know anything with certainty, and we humans don't like uncertainty. We have a really hard time dealing with it. When we think something is true and we find out that it's not, it really gets us upset. We also have very limited intuition for probability, just regular old probability. I mean, even among statisticians, they don't even agree on what a probability is. It's like some statisticians say probability is a relative frequency, and everything in my presentation, by the way, defined probability as a relative frequency. But then Bayesians define it different. They don't define it as a relative frequency. But I can't even tell you what they define it as because they don't agree either. So they have different definitions of probabilities. And so what are regular people supposed to do? That's tough. But then conditional probabilities, that's even harder. That's really hard. We have no intuition for conditional probabilities, and a p-value is a conditional probability, which is why the wording matters so much and where you put commas matters so much, and it just completely changes what it means where you put that comma. So focusing on p less than 0.05, it's just not enough information. I mean, at one point I had a slide where the title was the fault lies not within our statistical stars but within ourselves, but then I thought that was too cute, so I took it out. But I think it is true. It's like it's not the p-value's fault. It's our fault because we're trying to ask it to do too much, and this is just a really hard problem. So what do we do? Well, the first thing is just don't ignore the issue. Realistically, we cannot change everything that we're doing overnight, and we don't really need to, I don't think, but we can't. A lot of our projects are underway. They have approved designs and analysis plans. Not all of our clients are necessarily aware of these issues or focused on them. There appear to be some other things that our federal clients are focused on. I don't know why. But so it's not easy to just wholesale change what we're doing. But I think we can take some simple steps. There are things we can do. So we can just don't ignore the issue. We can avoid saying things in reports that are just flat out wrong. And so you could go to the ASA statement and it's 25 things of things not to say, and then maybe run a thesaurus on them, and you can see all the things that you shouldn't say. So just try to avoid saying things that are wrong. Another thing we can do is we can draw on more sources of information other than statistical significance in describing and interpreting our findings. And I think we really do this to a great extent now. I don't think that there are a lot of studies at Mathematica where our inference is based purely on a p-value, but we still might lean too heavily on p-values. And so we need to be conscious of that. We need to make sure that we're making an argument about the believability of our findings and the importance of our findings that is based more than just a p-value. There should be more to our argument than a p-value. So those are two things that I think we can do right now. We don't need to redesign a study or anything like that. We can do those things now. Other things that we can do that would be a little bit more, but not too much more, we can present some other error rates. So we could try to calculate some false discovery rates drawing on information from outside the study. And because that information you're drawing on from outside the study, like if you go to the What Works Clearinghouse or the Home Visiting Evidence Review or some of the other evidence reviews out there, and you look at a distribution of impacts, you know, it's a little squishy. And so you wouldn't want to hang your hat on one number. You'd probably want to say, well, if the probability of effectiveness is 0.1, this is what the false discovery rate is. If it was 0.3, this is what the false discovery rate is. But just give people a sense that the false discovery rate is not the p-value. Give them a sense that it's something else. And we can talk to clients about the issues and figure out ways to address it in the context of each project. Another thing to do is we just need to think more carefully about uncertainty. We need to think about what is the right balance of errors in a given context, in a given study. Is it controlling the false discovery rate at 5%? Is that really what we need to do, or do we need to worry more about missing impacts? And that's going to depend on the context. Another thing that we can do is we can try to provide more information. So we can report confidence intervals, we can report those false discovery rates, false non-discovery rates, Bayesian posterior probabilities, which is a related concept. I haven't talked about type M and type S errors, which is something proposed by Gelman and Carlin in 2014, but this is kind of a sneak preview of a future brown bag where there's going to be a brown bag where those errors are discussed. So I'm just giving you a heads up that there are other error rates that are out there that you could try to report or try to control. Something else that we could, in theory, do, I've never had an opportunity to do this myself, but we could focus on context-specific, decision-focused loss functions. So this would be in a case where our research is trying to inform a specific decision for a client. So it's not so much a broad finding for all of science, but it's trying to inform a very specific decision. And we could conceivably develop sort of an error rate or a criteria, an objective function specifically for that client and figure out the design parameters based on that. That's a little hypothetical. Another thing to do is stuff we already do. We try to use the best feasible study designs, high-quality data, QA, diagnostics and sensitivity analyses. This is all getting at the idea that the credibility, the believability of a finding is affected by non-random sources of error as well. So the p-value is focused on random sources of error, but non-random sources of error affect us too. I was working on a study recently, well, and I could say this at any point in the last 15 years, but I was working on a study recently, and we had a statistically significant impact estimate, and I said to folks on the team, the odds of you making a mistake is a lot higher than the odds of a program having a positive effect. So this is wrong. go figure it out. And it turned out it was right. But it's important to do very thorough QA, all the things we do to ensure quality, because it really is true that it's more likely that we're going to make a mistake than it is that a program had a positive effect. Another thing to do, which I think we do, and I'll try to stop this soon, is clear communication. And this is something that, some of these things you can't do right away, but it's something to keep in mind for the future. So if possible, have a pre-study design assessment of client needs. Try to understand how a client is going to use the findings and what their tolerances are for different types of risks. So are they concerned more about the false discovery rate or the false non-discovery rate? What's the mistake they're trying to avoid, and what's the alternative to using research to make the decision, if a decision is being made? Will the findings inform a decision, or is this just sort of like a general, this is for science kind of research project? This is important to just understand, so make sure we understand it from our clients. And then another aspect of communication, include in reports purposeful, systematic, and accessible discussion of the credibility of findings. So we do this a lot now. Like, we have our sensitivity analyses, our diagnostic analyses. We talk about our design. You know, we're talking about how this is a good study and you should believe it. But we could be just a little bit more purposeful in thinking about this in the context of this statement about p-values. So that it is good to say, okay, we've got statistical significance, that's one thing, but then we've also got all these other things that affect the believability of a finding. So have a clear discussion about what is the believability, the credibility of a finding, and then another discussion, which we often do now, about the substantive importance of a finding. So it's important not just because it's statistically significant, but also because it is of a certain magnitude. And there's like a paper, the name is sort of going out of my mind, but there's a paper written for IES that gave several criteria for thinking about interpreting the magnitude of impacts and whether they're substantively important. So you could use a cost-benefit analysis. You could think about closing gaps between two groups, like this impact would close half the gap between males and females and whatever. Let's see. And then also we need to just include in the report all the information that's necessary to assess the findings. Another thing that we should do is we should try to avoid replacing our old mistakes with new mistakes. So one thing that we could do is we could just throw out p-values and focus on magnitude. We could say the magnitude of the impact is big, so the intervention works. But that's actually just as bad, if not worse, than focusing only on p-values. Size matters, but it's not the only thing that matters. We should still be worried about the possibility that the impact is due to chance alone. The fact that the p-value doesn't tell us the probability that the impact is due to chance alone doesn't mean that the probability that the impact is due to chance alone is uninteresting. That is interesting. That is important. We should worry about it. And so study power and random mistakes, they matter. So we shouldn't just focus on magnitude of impacts. Another mistake we can make is like, well, everybody says Bayesian is great, so if we just do that, we'll be okay. But it turns out that actually we can avoid the difficulties with p-values even if we define a probability as a relative frequency. Everything in this presentation defines probability as a relative frequency. And there are some pitfalls for Bayesian analysis as well. You have to pick a good prior. You have to have a good model. Flat priors, which means basically you assume that the impact could be anything between minus infinity and positive infinity, all with equal probability. That would be a flat prior. That is equivalent to a one-sided frequentist p-value, and I don't mean that as a good thing. So Bayesians need to be careful about their priors. Alrighty, thank you everybody.